Let's now consider the vibration of a circular membrane. So instead of having a rectangular membrane, we now have a circular membrane. And we will use polar coordinates. No, the radius of this membrane is called capital R. And it's natural for us to use the Laplacian in polar coordinates instead of rectangular coordinates, as we did for the rectangular membrane. So in this case, the wave equation takes the following form. Moreover, since we assume that the plate will not deflect at the boundary here on this membrane, we assume that the displacement at this boundary is equal to 0. Moreover, we will also assume that the displacement or deflection, if you want, is equal to some function which is only dependent of the radius r. And in this case, it's rather trivial to see that the solution will not depend on the angle value theta. So therefore, this term will vanish. So we get a more simple wave equation to treat. So our problem is to find displacement u of r theta, rt, where t is the time. In addition, we will assume that the initial velocity, is also a function of r. So this is the initial velocity. That is the partial derivative of u with respect to t at time t equal to 0. We proceed exactly as we have done many times before. We use the method of separation of variables. Since the solution is dependent of r and t only, we start with assuming that the solution is a product of two functions, one which is only a function of r and another which is only a function of t. This is a standard way of using the method of separation of variables. And in this case, we obtain, as usually, two equations, two ordinary differential equations, and this k is some constant, and lambda is also a constant. Lambda is equal to ck, where c is the parameter or the constant in the wave equation. This equation is some Bessel type equation, and let's show how this is a Bessel equation. If we use the following substitution, put s equal to k, the constant k, multiplied with the radius r, then we obtain that 1 over r is equal to k over s. And by differentiating, we obtain the following equation. So by using this substitution, we find the Bessel equation. So this is in some way the Bessel equation, or it can be described by the solution of a Bessel equation, rather easy. The solution of this equation, the double star, which we have here, is, as we have told before, some constant a multiplied with j0 of s. This function, this Bessel function, which we showed you earlier, And since S is KR, we can describe this solution by R instead. So recalling that U is this product, and we use the boundary condition that at the boundary the solution U is equal to 0, we find that the W of capital R is also equal to 0. And this means that this A0 of KR is equal to 0. And it also means that this value must be some 0 of this Bessel function. So we are only considering cases where this constant k is equal to some value such that km, we can call this value km, multiplied with capital R is equal to the mth 0 of this Bessel function. So this is another way of writing it. And we see that W of R, this solution, must be of this form. It's dependent, of course, of the value m, or the mth 0, in the following way, which, as we have shown earlier, this function is equal to J0 of KMR. And inserting the value of Km, which you have here, we get this. So now we have the solution of this ordinary differential equation involving the W function. In addition, we have another ordinary differential equation. Let's just remind you about this. We had two differential equations. This equation, which we have considered now, and we also must have this ordinary differential equation satisfied. And recall that lambda in this equation is equal to c, which is a known constant in the wave equation, multiplied with this km value. We are only consider values of k such that it corresponds to this km values. So therefore, lambda should be some lambda m equal to ckm. And we know that km is alpha m over r, so this lambda should be c alpha m over r. And in addition to this, we know that the solution of this ordinary equation is a trigonometric solution of this type. This is always the case, but now we know the values of this constant lambda. It should be of the form lambda m. So what do we have? We have this type of solutions. We can index them as follows: um, which is a product of these two functions. This function is equal to J0 of this guy, and gm of t is equal to this type of equation. The only unknown are these am and bm. So the total solution is exactly as for other type of solution we have considered of this form. It's an infinite series where we sum all such terms and choose a, m, and bm in such a way that it satisfies our initial conditions. And the initial conditions are as follows: u are at time equal to to 0, this infinite series equal to the initial condition. And we know that alpha m is a function of this, is described by this formula. And these other constants bm is found in a similar way, where we take into account the initial velocity instead of the initial displacement. We are not going so much into details here, but it's really trivial to do this in the same way.